So I'm really pleased to be here to take part in this 60th birthday celebration of Professor Sundar, and I want to sincerely thank the organizers for inviting me here. So when I about almost 30 years ago, when I was about to start my career, I was quite fortunate to share an office with Sundar for almost 2 years. I don't think I realized at that time that I was sharing an office with a great mathematician, but still I think we used to discuss and he tolerated me, and we managed to write one or two papers during that time. And I'm going to speak on one of those, and I'll also make some remarks about the other paper, but overall it was a great educational experience for me and helped me quite a lot in the beginning. So one of those papers contains some conjectures which were later on we found out were formulated by some other people as well in some equivalent forms, and the main problems are still open, and so I just want to familiarize maybe people who are not familiar with this area little bit about these problems. So I think it starts with I have not written down everything, so I'll just say a few things which I have notes with me, and maybe I can explain without writing anything some of the things that I have with me. So I think the starting point of this is perhaps the Hadamard inequality, which is just a very simple bound for the determinant of a positive semi-definite matrix, and it is so this is my notation for Hermitian positive semi-definite matrices. I am also comfortable with real symmetric positive semi-definite matrices. Hermitian and complex doesn't add much to it. Okay, this is my notation. So if A is a Hermitian positive semi-definite matrix, then the determinant of A is bounded above by the product of the diagonal elements. This proved in 1893. Maybe it has some prior references also, although it is known by the name of Hadamard. And it was a very popular inequality at that time. I think Muir has a treatise on determinants, and it lists quite a few papers, close to 100, around 1920 to 1930, 40, and a great area of activity on this inequality. One can sort of prove, there are various proofs known, or it's not a difficult inequality to prove. One easy proof is that I will be using this idea quite a bit, that you can normalize A to a correlation matrix, namely you just make ones on the diagonal, and that doesn't affect the inequality. It is enough to prove it for a correlation matrix. And for a correlation matrix, you can just use the arithmetic mean, geometric mean inequality for the eigenvalues, and that will immediately give you this inequality. So that is one proof of this. So I'll be concerned with some generalizations of the Hadamard inequality. Particularly, there are several generalizations, and I'll be concerned with one called Oppenheim inequality, proved in the mid-1920s. And it says, so here I'm using this notation for the entry-wise product, or the Hadamard product, sometimes also known as the Schur product, of two positive semi-definite matrices. And it is well known that if A and B are positive semi-definite, then the circle product is also positive semi-definite. And Oppenheim inequality says that the determinant of A Hadamard product B is greater than or equal to the determinant of one of them times the product of the diagonal elements of the other. And if you take B to be the identity matrix in this inequality, then you recover the Hadamard inequality, because then you get, this becomes 1, and here, since B is the identity, you get just the main diagonal of A, and that becomes the determinant of that becomes the diagonal product of A. So that is how it captures the Hadamard inequality. I think we were in one of the papers that we wrote at that time was quite a bit inspired by this inequality. There is a certain majorization relation known for eigenvalues of a symmetric matrix. So if you have a symmetric matrix, the eigenvalues majorize the diagonal elements, and this was a result by Schur, that if you take lambda 1, lambda 2, lambda n are the eigenvalues, and the diagonal elements a11, a22, an, then their sum is equal, which is the trace, and there is a chain of inequalities, that the largest eigenvalue is greater than or equal to the largest diagonal element, then the largest plus the second largest dominates the sum of the two diagonal elements, and so on. This is the relation known as majorization. So the diagonal of a symmetric matrix is majorized by the vector of eigenvalues. And in one of our papers, we had a similar statement that if you take a correlation matrix B, then there is a majorization relation between eigenvalues of A Hadamard product B and A. So the eigenvalues of A Hadamard B are majorized by the eigenvalues of A. So this is the generalization of the earlier result, again because you can take B to be the identity matrix. And from there, we proved one inequality for eigenvalues of A Hadamard B and eigenvalues of A, of which this is the final case. That means there is a similar inequality with partial products. So you can think of this as the product of all the eigenvalues of A Hadamard product B, and this is the product of all the eigenvalues of A. But something more is true. You can start with the least eigenvalue here and the least eigenvalue here and the product of the least two and the product of the least two. And here you put the least diagonal elements. So there's a chain of inequalities. This was a conjecture at that time, and then one of our things in that paper was to settle that conjecture. Okay, the second inequality, generalization of Hadamard, is this inequality for generalized matrix functions. So I take, this is a generalized matrix function defined here. So you have a subgroup of the symmetric group and a character, and then you define this. And this result is again attributed to Schur, and that this is dominated by chi of identity times the determinant of A. And in particular, if G is the whole group, Sn, and chi is irreducible, then this has been called an immanent. And so Schur proved that the immanent is greater than or equal to this chi of identity times the determinant. Again, here something much more general is true, that if you take any function, suppose I replace this chi sigma by just a function C sigma without any condition, and if that function is non-negative on positive semi-definite matrices, okay, let me repeat, I put here any arbitrary function of sigma. If it so happens that that function is non-negative on the set of positive semi-definite matrices, then it is always greater than or equal to the determinant. I'll just normalize so that at identity it is 1. So much more than this is true, and so this kind of inequality is, and the proofs are not difficult here. So in this case, the proofs are not difficult. Okay, one of the things I want to now talk about is similar inequalities are conjectured to be true for the permanent. Here in this case, you must use the opposite direction. And that will be one inequality that is still conjectured to be true and open. And that is the conjecture I am referring to as the 25 years of a permanent conjecture. Because in that other paper, which I am going to talk about mostly, this was written down for the first time perhaps, and then some comments were made. And so that would be called as permanent Oppenheim. And so permanent here, and I'll state it again. And similar inequality here is open, that all these immanents are bounded above by the permanent. This so-called permanent on top conjecture, or the permanent dominance conjecture. Now this is just an example of a permanent. So the permanent is also a generalized matrix function. You just take the whole group, and I think I should point out that in the previous case, when you take the subgroup to be just the identity element, then this specializes to the Hadamard inequality. So that is how it generalizes the Hadamard inequality. And then the permanent is the sum of the diagonal products, and the definition is almost simultaneous with the determinant. But the real development took place in due to a conjecture of van der Waerden, which I'll mention later, about permanent of a doubly stochastic matrix is minimized when all the elements are equal. It is the centroid of the set of doubly stochastic matrices, and that was a conjecture which was open until it was resolved in the early 80s, and that generated a lot of interest. And so computation is not very easy. I mean, you just have to use, there are some algorithms based on inclusion, exclusion. In fact, computation of permanent is a model computer science problem nowadays. It's taken as one of the key problems, and there are many deep results known in this area, and also Monte Carlo methods for approximating the permanent and so on. Okay, now to unify all these things, I need one particular definition, which is the key definition, and this is called Schur power matrix. Again, this goes back to the same paper of Schur. I'll comment on this a little later. And the term Schur power has been coined by Russell Maris in the 80s. And the idea is like this. You take the tensor power of A with itself n times, and this is going to be an n to the power n by n to the power n matrix. It is going to be indexed by all sequences I1, I2, In of 1 to up to n. From there, you come down to a certain principal submatrix, namely the principal submatrix which is indexed by the permutations. That will be of order n factorial by n factorial, and that is the matrix I am calling as the Schur power matrix. So the definition is like this: it's a principal submatrix of this. It's a certain principal submatrix where so the typical entry is given like this: if sigma and tau are two permutations, then the corresponding sigma tau element is a certain diagonal product of A, given by A sigma I tau I. And many of the properties of permanent of a positive semi-definite matrix become obvious because of this construction. For example, if A is positive semi-definite, then permanent is non-negative. That's not obvious, but it becomes obvious after this construction, because if A is positive semi-definite, then the Schur power is positive semi-definite. And if you take any row sum, if you fix sigma and take sum over tau, you get the permanent. So permanent is an eigenvalue of this matrix with the eigenvector equal to all coordinates 1. And many other properties become obvious. For example, if A dominates B in the Lohner ordering, positive semi-definite ordering, then the permanent of A is greater than or equal to permanent of B. That becomes obvious from this definition. And I have just given an example. This is not very helpful. I have not taken a Hermitian matrix, so you don't get a clear idea of what is going on. But if you order the permutations this way, then this is going to be the Schur power matrix. But at least you can see that all the row sums are equal to the permanent, so are all the column sums. And if you take a sum with weights +1 and -1, column sums with weights +1 and -1 depending on the parity of the permutation, then you get the determinant. So the determinant is also an eigenvalue of this Schur power matrix. And one more thing you can say is that any immanent is in the field of values of this Schur power matrix. That's also not difficult to see. You just take a suitable vector x indexed by permutations and take inner product of pi a times x with that vector, then you recover the immanents. So all immanents are sitting in the field of values of this matrix. So it is interesting to look at this matrix, and there is a little bit of history about this, that when we started looking at this problem, I think I just want to tell you that perhaps at that time this immanent conjecture was known. It's a conjecture due to Lieb in the mid-60s that permanent dominates all the immanents. But the Schur power construction was not very well known, and I think I was explaining this to Sundar about that immanent problem, and I think within a few hours, or at least in a day or so, he came up with the entire construction of the Schur power matrix, which was quite unknown to us at that time, and he also formulated this main conjecture. I still remember, hardly a matter of a day or so. And then we started reading this paper, it is in German, and we found out that at some place, Schur does prove indeed that determinant is the minimum eigenvalue. He doesn't call it a separate lemma or a theorem, but he does prove it completely. And this was a surprise to many people at that time, because this was listed as an open problem even at that time. This is, I'm talking of even the 83 or something like that. That it was always mentioned as an open problem that the determinant is the smallest eigenvalue of the Schur power matrix and the permanent is the largest eigenvalue. So the determinant is the smallest eigenvalue is essentially proved in Schur's paper. Again, the proof is not very difficult. And the main conjecture, the main unsolved problem in this area now is that the permanent is the largest eigenvalue of this matrix. And this is, so we formulated at that time, and later on we found out that there is a school of Marvin Marcus and his students in Santa Barbara who were working on this permanence as a whole, and Schulz happens to be a student of Marcus. And in his PhD thesis, he had worked on this problem, and I think he says that he formulated it right in his thesis. But in print, it came in this paper, where both these problems are mentioned as open problems. Determinant is the smallest eigenvalue, and permanent is the largest eigenvalue. And we also formulated it, and we were able to prove it for n less than or equal to 3. And now I think up to 4 perhaps it is available, but there haven't been any major developments. And so this is the main problem, that if A is a Hermitian positive semi-definite matrix, then permanent is the largest eigenvalue of the Schur power matrix. This conjecture, as I said, it dates before the this maximum eigenvalue conjecture, and this is generally known as the permanent on top conjecture or the permanent or dominance conjecture. And several special cases, a large group of people have been active on this because of the connections with group theory. Because you can isolate a special immanent that you like and then prove inequalities for that. And refinements are there. For example, if you take immanents which come from a young tableau which looks like a single hook, these are called single hook immanents, and permanent and determinant are indeed a single hook immanents. Then there is a chain of inequalities for those immanents that is known. So stronger statements are known for special immanents, and up to n equal to 8 or something, all immanents have been taken care of. And there are a large number of papers on this. In fact, Leib's celebrated result, this is a generalization of the Fisher inequality for matrices, which is if you put determinant instead of permanent in the other direction, that is a well-known generalization of Hadamard inequality known as the Fisher inequality. And this is the permanential Fisher inequality. And this is also can be thought of as an immanent, what appears on the right-hand side. So Leib, in fact, proved this. And I think this is one of the few cases which are known in general for the this conjecture in general, for all matrices of all order. Okay, so I'll briefly mention this van der Waals-Igoryshev-Folkman theorem. There are some connections when I talk to it, not direct connections, but maybe some ideas, that if A is an n cross n doubly stochastic matrix. So here by doubly stochastic, I mean all the entries are non-negative and the row and column sums are equal to 1. Then the permanent is dominates the permanent of Jn, where Jn is the matrix with all entries equal to 1 over n. So there is a certain duality between the properties of permanent on non-negative matrices and on positive semi-definite matrices. And for example, if A also happens to be positive semi-definite on top of doubly stochastic, then this is immediate, because one can show that A dominates Jn in the loner ordering. That is not difficult to prove, because Jn is a rank 1 matrix, and it's easy to show that A dominates Jn. And because of what I said earlier, that if A dominates Jn in the loner ordering, then the permanent of A greater than or equal to permanent of Jn. And so something which is non-trivial for non-negative matrices becomes easy when you specialize to non-negative matrices which are positive semi-definite. And similarly, going back to this permanent on top maximum eigenvalue conjecture, this is also immediate if A is positive semi-definite as well as non-negative, entry-wise non-negative. Because then this becomes really a non-negative matrix with equal row and column sums. So by the Perron-Frobenius theorem, if you have a non-negative matrix, then any eigenvalue which has a positive eigenvector is the maximum eigenvalue. And I think in our discussion, what I recall that we did notice this duality and we spent some time on that, and whether this gives some method to attack the problem. I think Sundar had observed at that time, and I have forgotten the proof of that, that under some non-degeneracy condition, if permanent can be shown to be a simple eigenvalue of the Schur power matrix, then it is the maximal eigenvalue. I think Sundar might recall that we had discussed about this. This has not appeared anywhere, but it is enough to show that, of course, you have to assume perhaps a non-diagonal matrix. If A is a non-diagonal matrix, if one can show that permanent is a simple eigenvalue, has multiplicity 1, then it follows somehow that it is the maximal eigenvalue. And in some work later on, Souls has picked up on this idea independently. He shows that if you take the eigenvector, constant eigenvector, all equal to 1, and if you can extend it to a unitary matrix, such that with that unitary similarity, this becomes non-negative, entry-wise non-negative, then of course this conjecture will follow. And Souls essentially claims that that is the only way it can be done. It has to happen. So there must be a unitary matrix with starting vector all equal to 1 normalized, so that the unitary similarity on this gives you a non-negative matrix. So that paper of Souls, which was again in the early 80s, became quite well known. Yeah.
How does that gel with the proof of the 3 by 3 case of Souls conjecture?
Excuse me? 3 by 3 case, yeah?
3 by 3, we know that Souls conjecture is true.
Yes, yes.
So are you saying that everything is unitarily equal to something which is positive?
There will be a unitary matrix. It may depend on A.
Yeah.
Yeah. Souls was hoping that maybe by some combinatorial method you can get a hold of a unitary matrix, because there is a lot of structure in this pi A matrix. So Soule's hope was by some combinatorial type of, yeah,
If the latest source conjecture that you mentioned now
yeah.
is true, then it would mean that any 3 by 3 positive semi-definite matrix must be such that its power matrix can be unitarily conjugated to be entry-wise positive.
Yes,
Is that true?
yes. That's what it says.
Is that statement true?
I don't know. I mean, but since the conjecture has been proved, okay. So now, okay. So I think, sorry. Okay. So this is the conjecture that I was referring to in my title, that the permanential Oppenheim inequality is true, and it is sufficient to prove this for correlation matrices. Okay, just a small remark that the maximum eigenvalue conjecture does imply the permanential Oppenheim, and this is because of a simple observation that if you take two matrices and denote this, let lambda 1 denote the largest eigenvalue, then lambda 1 of A Hadamard product B is less than or equal to. This is a simple inequality to prove, and because of that, if you take the lambda 1 of pi of A Hadamard product B, then this is pi of A Hadamard product pi of B, and this is going to be less than or equal to, because of this inequality, largest eigenvalue of pi of A times all diagonal elements of pi B are equal, and they are equal to this product. So I get this inequality, and now if the maximum eigenvalue conjecture is true, then this is the permanent of A Hadamard B, and this is the permanent of A, and that is how you get the permanent Oppenheim. So it is believed that whatever difficulty is there in the main conjecture is perhaps in this conjecture, but this conjecture looks very straightforward. I mean, there are no non-trivial constructions. It's a very tempting thing to show, but perhaps the real difficulty is in this conjecture itself. Okay, there are some related problems which we also formulated there. For example, if you take a unitary representation, several other matrices can be conjectured to have permanent as the largest eigenvalue. I've written it one inequality here, but this is more matrix theoretic, that if you take the permanential cofactor matrix, this is the permanent of A, delete row I and column J, and then Aij times that. So this is also a doubly stochastic, I mean the row and column sums are all equal to the permanent, because permanent has a Laplace expansion. And so this is also a matrix with eigenvalue permanent of A, and it can be conjectured that here also permanent is the largest eigenvalue. The interesting thing here is it's an n cross n matrix, not a big matrix. And in fact, we can do a similar thing with higher order compound matrices, and this has been done and conjectured by Pate. Pate has written a lot of papers on the immanential conjecture, and he has quite a few results. And he has formulated recently this conjecture that if you take the kth compound of A and Hadamard product, so I'm not defining the compound matrix, it's just the matrix of subpermanents with all k rowed minors, k rows and columns. And if you take its Hadamard product with the n minus k order compound, then again permanent A is the largest eigenvalue. So our earlier case was just the case where you had 1 and n minus 1, and he has some partial results. Okay, now I want to publicize one conjecture which I had formulated later on, and so I might come back to some points about the earlier conjecture later. So this is not directly related, but this is something which is interesting. So there are various Q analogs have been proposed for the permanent, which unify the permanent and the determinant. I'll mention two of them. Here is one Q analog that, just look at the definition. So you take a parameter Q, which typically will be in the unit disk, but I will concentrate on just the unit interval, not -1 to 1, the interval -1 to 1. And in that interval, one can define this function. Here, L of sigma is the number of inversions of sigma. And it is well known that the number of inversions of sigma, they have the same parity as the permutation, sign of the permutation. So in particular, so this is a function which generalizes the determinant and the permanent. So when q is equal to -1, you get the determinant. And when q is equal to 0, if you interpret 0 to the power 0 as 1, then only one term you get, and that is the main diagonal product. And at q equal to 1, you get the permanent. And it is well known that this function is also positive on positive semi-definite matrices. So in fact, I have not defined, one can naturally define a function which is positive definite on the symmetric group. You just take any function and then form an n factorial by n factorial matrix with the entry. If the function is f, then the typical element will be f of sigma tau inverse. And if that matrix is positive semi-definite, then we call the function to be positive definite on the symmetric group. And it turns out that this function is positive definite on the symmetric group. In fact, if you look at just this function on the symmetric group and form that n factorial by n factorial matrix, it acts like a distance matrix. It has zeros on the diagonal, and it has some interesting properties. But with this, I think it was a paper in Communications of Mathematical Physics that if A is a positive semi-definite matrix, then permanent is non-negative. But there are other proofs known by just using properties of distance matrices. And the conjecture I want to just recall here is that if A is positive semi-definite, then permanent QA as a function of Q is increasing in -1 to 1. So this was inspired obviously by this chain of inequalities. So this is the Hadamard inequality, and this goes back to Marcus. This is the permanential Hadamard inequality. You can say that this is again one of the first cases of the permanent on top conjecture, because this is again a case of an immanent, this is a case of generalized matrix function, and permanent dominates this. I think the Leap's inequality which I stated was a generalization of this inequality. So this is the permanential Hadamard inequality, and the conjecture is that there is a monotonicity among all these three cases. This is not, there is no work on this as far as I know. It's in fact here it is very steeply increasing. It's very fast in this 0 to 1. And again, for 3 by 3, one can write down special inequalities and prove, but there are no general cases. I'll mention one more Q analog. So Weir-Jones has proposed this another Q analog. This is, I'm calling it, instead of Q, I'm using alpha. So here I'm now putting n minus the number of cycles. So this is also a generalization of the permanent and the determinant. And I'm using determinant, but this is just because of convention. And so when alpha is equal to -1, again it is equal to the determinant, because this again reduces to the sign of the permutation. And if alpha is equal to 1, then it is the permanent. And it occurs in series expansions of this, for example. You get naturally these functions. And there was a conjecture about this, that if A is positive semi-definite, and if alpha is between 0 and 2, then determinant of alpha is greater than or equal to 0. And I was told this was proved false. Brandon has quite a few influential papers in the last 10 years or so. Some of his work has been summarized in a long paper in the bulletin of the AMS using hyperbolic polynomials. He has settled many conjectures recently, and including some permanent conjectures. And this was proved false. Actually, he proves that there are some isolated points where it fails. And apparently this is considered quite surprising by the people in this area. I don't know much about it. I just wanted to point out this is quite recent. Okay, now just to summarize, going back to one approach which was proposed by Souls also for the permanent on top conjecture. Recently, Zhang has just summarized some development. There haven't been any major developments as far as these problems are concerned. Zhang has again summarized some of the developments and has given one technique, like because van der Waals conjecture was proved by a kind of an optimization. At least the starting point was an optimization idea, that you want to minimize the permanent over doubly stochastic matrices. It's a compact convex set, so there's no problem, there are minimizers. So if you take one minimizer, then it can be shown by Lagrange multiplier and simple methods that all its permanent cofactors must be greater than or equal to the permanent of the matrix. So this is for a non-negative matrix. And then our job is to identify such matrices. And at that point, one uses the Alexandrov inequality, which was again the second main technique, which was not known until that time. It was in the literature, but the connection with permanent was not known. So then one uses the Alexandrov inequality to settle, characterize such matrices where the permanent cofactors dominate the permanent. Something similar can be tried here. So you can take this function A Hadamard product X, and this is an equivalent version, formulation, perhaps if and only if. So you try to maximize this permanent of A Hadamard product X, and if one can show that the maximum over correlation matrices is attained only at the correlation matrix with all entries equal to 1, then the conjecture is proved. And Stang has made some remarks about a maximizing matrix. If MA is a maximizing matrix, then these are inspired by similar properties in the case of van der Waals conjecture, there is some parallel. So if it is the maximizing matrix must be singular, so that's the first step. And if it is irreducible, then any maximizing matrix is irreducible and so on. But these are some partial results. And using Lagrange multiplier, one can show something similar to what I said earlier about the van der Waals conjecture, that if A is a minimizer in the case of doubly stochastic matrices, then all the permanent cofactors are greater than or equal to the permanent. And here something, in fact, then it so happens that if the matrix is entry-wise positive, then all the permanent cofactors are in fact equal. And something similar can be done here, that all these principal submatrices. So here there exist reals depending only on A, such that for any maximizing matrix, this inequality holds. So the hope is that one can work further with these inequalities and get some idea about the maximizing matrix X. This is also in line with what Schulz had proposed, a similar approach. Q analog?
If you take the when you take, if you order the Young diagonal according to the natural order, and if you take the representation for a bigger one, then the norm of that matrix larger than the other for a positive matrix. Do you understand what I'm saying?
You mean the corresponding immanent?
Not immanent. If you see, for every representation of the symmetric group, you apply the representation to your power matrix. Then you get an associated positive matrix. You start with the positive matrix, take its power matrix, and apply the representation to it. So the norm of that matrix under that representation is that monotone in this order is what I'm saying.
No, norm, which norm you are taking? The eigenvalue. Which norm you are taking?
The operator norm. Largest eigenvalue.
No,
And in the sense that the power is largest.
okay.
Determined the smallest. Or even immanent.
No, immanent, then I think it is related to that single hook where they are ordered. Immanents are ordered for the single hook immanents as the hook length.
Not using for any two young
Yeah, any two young diagonals.
is not normal.
No.